In this video, we're going to be discussing one particular type of equilibrium reaction that has to do with solubility. But I would like to start off by asking you to try this problem on your own, because most of what we're talking about today is absolutely nothing new, is really just putting some new terminology on things when we're talking about this one particular type of equilibrium. So you're given this equilibrium that is lead 2 chloride dissolving in water to form aqueous ions. You're given the value of the equilibrium constant and asked to calculate the equilibrium concentrations of lead and chloride ions when lead 2 chloride is placed in pure water. So this is just going to be a set up an ice table and solve situation here, nothing new. So take a minute or two and try this one on your own. So to solve this, we'll want to set up an ice table. Just like we've done before. And we want to think about what is initial, what is change, what is equilibrium in this situation. So first thing to recognize is that our reactant is a solid. So because it's a solid, we don't need to think about that since its concentration will be constant. So our initial in this is before any reaction happens. We're told that we're just putting our solid stuff in some water, which means initially we have no lead and we have no chloride present in our system. Now, as this moves towards equilibrium, we're going to have to produce some product to get to equilibrium. So both of these concentrations are going to increase, but we don't know by how much. So we leave it in terms of X. And thanks to that coefficient of 2 in front of chloride, for every X molar lead we produce, 2X molar chloride will be produced. So that means at equilibrium, we will have a concentration of X for lead and 2X for chloride. So to solve for X here, we need our equilibrium expression. K is products over reactants. So we have our lead that is aqueous. So we will take the concentration of lead ions, and we have chloride is aqueous with a coefficient of 2. So we'll have Cl minus squared. Our only reactant is the solid, which gets left out of the equation. So this is our complete equilibrium expression. So now we were given the value of K, so we can plug that in. We know that the concentration of lead at equilibrium is equal to X. The concentration of chloride at equilibrium is 2X, and that is going to get squared. And now this is something that we can solve. The only variable we have is X, so we can work on solving this. So 2X squared is 4X squared. Remember to square both the X and the 2. And if we multiply that by X again for our lead concentration, we get 1.6 times 10 to the negative 5th is equal to 4x cubed. So if we divide both sides by 4, we get 4 times 10 to the minus 6th is equal to x cubed. Cube root both sides gets us x is equal to 0.016 molar. So we need to remember that X is not necessarily what we're solving for. We were asked for equilibrium concentrations of lead and chloride. So those are the things we want to make sure that we are actually solving for. concentration of lead is X, so that's convenient from our ice table here. So that will just be 0.016. But our concentration of chloride is 2X. So if we multiply that by 2, our chloride concentration at equilibrium will be 0.032. So absolutely nothing about this was different than anything you've done before. But when we're dealing with this particular type of reaction, which is commonly referred to as a solubility equilibrium, there are a few pieces of terminology to be aware of, and we can get a deeper understanding of what this system is, since we've already studied the concept of solubility. So what we need to recognize here is that dissolving is a reversible process. So a solubility equilibrium is always an ionic solid in equilibrium with its aqueous ions. So we wrote these types of reactions in our very first unit, in our solubility unit, as being reactions that go to completion, something that only goes one way. But really, these are reversible processes. The forward direction, going from solid to aqueous, is what we would call dissolving. And the reverse direction, going from aqueous to solid, is what we would call precipitation. Dissolving and precipitation are opposite processes, that they are the forward and reverse of the same thing. So we can and should really represent these as reversible reactions. They are an equilibrium process. And what we're really representing for this type of system to be at equilibrium is a saturated solution. So when this type of system is at equilibrium, that means that we have the maximum amount of solute dissolved in our system, which is what we call a saturated solution. When we have achieved as much dissolving, as much aqueous ions as we're going to achieve, there's going to be some solid left over in the system. And really at the molecular level, some of that solid is dissolving, but for every particle of solid that dissolves, aqueous ions precipitate out as well. So we have this balance that the rate of dissolving and the rate of precipitation are equal. So the equilibrium constant for this type of reaction has a special name. It is known as the solubility product constant, or KSP for short. So if I were giving you this problem, I would probably really label this as a KSP, but it is not any different than any other K value that we have talked about. The only difference, the only reason that SP is there is just recognizing that it's this particular type of reaction that we're talking about, that it is a solubility equilibrium that we're dealing with here. The concentration of a saturated solution is also known as the molar solubility. And that's another type of thing that is commonly used, that ice tables are commonly used to solve for. So if you're thinking about this type of reaction, the molar solubility is something that you often want to calculate, that you want to know what is the maximum molarity I can have for this. And that is just X in your ice table. So if you're asked for the molar solubility, it just solve for X is what you're doing. So in the example that we started with, we found the molar solubility, I just didn't explicitly ask you for it. So our value of X here is our molar solubility. I could have asked you to solve for that instead if I had done this example at the end of the video rather than the beginning. But again, it's something you already fundamentally know how to do, just labeling it a little bit differently, just different terminology. And one thing to note with molar solubility is that when we're comparing solubility, when we're saying that something is more soluble or less soluble than another substance, it is the molar solubility that we're comparing, not the KSP. They don't necessarily go hand in hand, depending upon what your equilibrium expressions look like. So when we say something is more soluble or less soluble, let's just stick with one. When we say something is more soluble, we mean it has a higher molar solubility. Not a greater KSP. Sometimes they go hand in hand, but not necessarily. So let's highlight this. More soluble means larger molar solubility.